Hello, my friends. Nice to meet you again. This is a question from Germany Mathematical Olympiad competition of 8th grade. In a country, there are many airports, and the distance between each two airports is different. Every day, there is an airplane taking off from each airport and flying to its nearest airport. By the night, one could count the number of airplanes that landed at each airport during the day, and found that, at most 5 airplanes landed at any one airport. Can you prove why? Why not give a try, and we will come back soon. This is a story problem. To give a mathematical solution, the first task is to translate the problem into mathematical language. What is its mathematical meaning? There's a point S, which is whatever airport we're talking about. Other airports are other points A, B, C, D, etc. If there is an airplane flying from a point to S, we connect it with S with a line segment. A line segment connected in this way, for instance, AS, should be shorter than the line segment connecting point A to any other point. The statement is therefore that, the number of such points A, B, C, D, etc., will not be equal to or more than 6. How to prove that? Since the point of the question is that, AS is shorter than any line segment connecting point A to other points, we should first make a so-called other line segment. So when we connect A and B, we get that AB is longer than AS. Of course, from perspective of point B, AB is also longer than BS. For the same reason, by connecting BC, one will get that, BC is longer than BS and BC is also longer than CS. This rule applies to any pair of adjacent points which are connected to S points. Now let's look at any of the triangles, ABS. Because AB is the longest side, so the angle ASB, which it subtends is bigger than 60 degrees. Regarding why the interior angle subtended by the longest side of a triangle is bigger than 60 degrees, we can talk about it later if you don't quite remember. At the moment, we just need to know that, in each of these triangles, the interior angle of the vertex where S is located is bigger than 60 degrees. Circling around the S point means adding up all these angles. So if the number of these angles is equal to or greater than 6, then their summation will exceed the angle of a circle, which is 360 degrees. This is impossible. So there are at most 5 points connected to point S with this condition, namely, at each airport at most 5 airplanes can land per day. Now, let's review why the interior angle subtended by the longest side of a triangle is bigger than 60 degrees. We can also use this triangle ABS to show it, where AB is bigger than AS, as well as BS. Therefore, we know that there exists a point D on the segment AB, such that AD equals to AS. We connect SD, and get the triangle ASD as an isosceles triangle. So angle ASD is equal to angle ADS. How big is the angle ASB, which is subtended by side AB? It is equal to angle ASD plus angle DSB. At the same time, the exterior angle ADS of the triangle SDB is equal to the summation of the two interior angles ABS and DSB. Therefore, we know that, angle ASB is bigger than angle ASD, and angle ADS is bigger than angle ABS. So the angle ASB is bigger than the angle ABS. In the same way, it can also be obtained that the angle ASB is also bigger than the angle SAB. The summation of the three interior angles ASB, SAB and ABS of a triangle is 180 degrees. Then the largest angle ASB must be bigger than 1/3 of 180 degrees, that is, 60 degrees. Can we quantitatively discuss the specific relationship between these three angles and three sides? Of course we can. That's the so-called law of sines. Normally, most students in 8th grade have not learned about the law of sines. However, if you have some basic knowledge of trigonometric functions, it is not difficult to understand a little about the proof of law of sines. Let's take the triangle ABS as an example to briefly demonstrate the situation of an acute triangle. The situations of right-angled triangles and obtuse-angled triangles are actually similar. This time, we plot the altitude SH on the side AB. In the right triangle ASH, we have that, SH equal to AS times sine SAB. Similarly, in the right triangle BSH, SH is equal to BS times the sine ABS. Therefore, the ratio of AS to sine ABS is equal to the ratio of BS to sine SAB. If we plot the altitudes on the other sides, we will get in the same way that they are also equal to the ratio of AB to sine ASB. And what is exactly the ratio? We plot the circumscribed circle of the triangle ABS. And by passing point A plot the diameter AK, whose length is labeled as AK equal to twice R. The circumferential angle ASK subtended by the diameter must be a right angle. The circumferential angles ABS and AKS subtended by the same arc are equal to each other. Therefore, sine AKS is equal to the ratio of AS to AK. So this ratio is equal to the diameter of the circumscribed circle of the triangle. These contents are already beyond 8th grade level. But there are always some genius students asking further questions. For example, the ground is a sphere. How can we use the content of plane geometry to prove this question? It is really not supposed to be asked by an 8th grade student, but if you asked, you are really smart. Indeed, on a spherical surface, the three sides of a triangle are no longer straight line segments, but geodesic line segments. The shortest distance between 2 points is also indeed measured on a geodesic. But never mind, on a sphere, the summation of the interior angles of such a triangle is bigger than 180 degrees. So it is even worse. Still, 6 or more airplanes cannot land at one airport per day. Thank you for watching, and see you next time.